All right, hello everybody. This is the very beginning of our series of Unit 5 videos for AP Chemistry. I'm just going to show you a few slides on vocabulary that you should definitely familiarize yourself with, especially before we start the chapter. If you could just read through these, take a moment to pause and read through and just make sure you understand the basic definition of each of these terms. All right, so 5.1 goes through reaction rates. You need to understand that some reactions happen quickly while others happen more slowly and depend on reactant concentrations and temperature. At the end of this lesson, you should be able to explain the relationship between the rate of a chemical reaction and the experimental parameters. And then also we are going to learn through this lesson that the kinetics of a chemical reaction is defined as the rate at which an amount of reactants is converted to products. And the rate of change of reactant and product concentrations are determined by the stoichiometry in the balanced chemical equation. And the rate of a reaction is influenced by reactant concentrations, temperature, surface area, catalysts, and other environmental factors. So the rate is a change in something per unit of time. In chemistry, we call it a reaction rate, and it measures the way substances change by looking at change of the reagents or substances in the reaction. We can look at mass, volume, moles, and molarity to determine this change. Just the overall formula for reaction rate is going to be the change in mass of the reactant or product over a unit of time. And keep in mind that the unit of time can vary based on how quickly the reaction takes place. For example, if you have a really fast reaction, you can use seconds, while if you have an extremely slow reaction, you can use units of time like years. So consider the reaction shown. I just want to go over different ways in which you can measure change for this reaction. So we have solid copper reacting with nitric acid, and it's creating 3 different products. So one way you could measure a change is the volume of NO gas produced, and you could do that by the displacement of water. Since NO is only slightly soluble, you could do that. You could also measure change based on the pressure change if you have it in a sealed container. And then the molarity of CuNO32 could be determined using a spectrophotometer, since copper nitrate is colored. And then you could also look at the loss of mass, because NO2 is gas, so if you're measuring your reactants and then measuring your products, it will decrease since that NO2 was released. And then also you could look at the pH of the solution, because nitric acid is an acid. As it converts into something else, you're going to have an increase of pH because you are losing some acidity in that reaction. All right, so using that same reaction, let's go over how to solve for rates of different reagents and also the overall rate of reaction. So again, this is using nitric acid and copper 2 nitrate from the reaction shown. And first we're going to calculate the rate of nitric acid at 50 seconds after the reaction occurs. So when we are determining the rate, we're going to take the final concentration and subtract the initial concentration. That will give us the change in concentration or amount. And we're going to divide it by the final time minus the initial time, or the change in time, and that will give us the rate of that specific reagent. So since we are doing HNO3, we're only looking for the change in concentration for HNO3. So final would be 4, initial would be 8. That's going to be the change in amount. And then the change in time would be 50 seconds minus 0, which would just be 50. So we have -4 divided by 50 is going to give us a rate of 0.08, and again that is meters per second. I'm sorry, molarity per second. And then we can do that for each change in time. So our rate for HNO3 for 100 seconds would be 2 minus 4 for our molarity, and 100 minus 50 for our time. So it would be -2 divided by 50, which would give us 0.04 negative molarity per second. And then finally, we can do for the last one as well. We have 1 minus 2 for molarity, and 150 minus 100 for our seconds. So it would be -1 divided by 50, which would give us -0.02 molarity per second. Now notice that the rate for reactants is negative because that amount is decreasing. So since our nitric acid is a reactant, all of the rates for nitric acid is going to be negative. So now let's do the same thing for our rate of copper 2 nitrate. So we have our concentrations of copper 2 nitrate, and then our times are going to be the same since they are the same timetables. So for copper 2 nitrate, we have a concentration going from 1.5, or going from 0 to 1.5, so it'd be 1.5 divided minus 0. And then our time would be the same, so 50 minus 0. So we're going to have 1.5 divided by 50, which is going to give us positive 0.03 molarity per second. Now notice the reactants are becoming products. So since we are looking at a product, your rate and your rate of reaction is going to be positive because it is moving towards our products. So let's go ahead and do that rate for the next two timetables. We have 2.25 minus 1.5 over 100 minus 50. So 2.25 minus 1.5 is going to give us 0.75. Divided by 50 is going to give us 0.015 molarity per second. And then the same thing with the last one, 2.63 minus 2.25 over 150 minus 100. So 2.63 minus 2.25 is going to give us 0.38, and then divide that by 50. It's going to give us 0.0076 molarity per second. So now for our rate of reaction, it can be defined in many ways, but the most common way to calculate that is going to be to take the rate of that reagent and divide it by the coefficient number. So if you are using HNO3 to find your rate of reaction, that means it's going to be a negative number, right? Because your concentration is moving away from that reagent. However, if you're using your rate of product, you're going to have a positive rate of reaction. So for this rate of reaction column, let's go ahead and use our product, which is copper 2 nitrate. So in order to find out our rate of reaction, all we're going to do is take that rate and divide it by 3 because our coefficient of that reagent is 3. So 0.03 divided by 3 is going to give you 0.01 molarity per second. The next one is 0.015 divided by 3 is going to give you 0.005 meters, or I keep saying meters, sorry, molarity per second. And then our final one, 0.0076 divided by 3 is going to give us 0.0025 molarity per second. So that's just a brief example on how to calculate the rate of reagents in your reaction. All right, so keep in mind that the rate of reaction can only be determined experimentally. So if you have this reaction shown, 2N2O5 decomposing into 4NO2 and O2 gas, you can see that in this graph, as the reaction is proceeding, the concentration of N2O5 is going to decrease because it is your reactant, and your NO2 and O2 are going to increase because these are your products. So they are going to change according to their coefficients in the balanced chemical equation. You can see that NO2 is increasing about 4 times as much as O2. Well, that is because NO2 has a coefficient of 4 and O2 has a coefficient of 1. So that is going to be relative to those coefficients in front of your products. So now let's talk about collision theory. In order for a reaction to take place, there are 3 things that must happen. The first thing is particles must collide. The second part is that particles need to collide with the correct orientation. And then the final piece is that particles must collide with energy that is greater than the activation energy. So there are 4 factors that we're going to talk about that influence that rate of reaction. The first one is concentration. Now, we should know that at this point, when you have a higher concentration, you're going to have more particles, which means you have a higher chance of collision. The next one is temperature. When you have higher temperatures, those particles are moving much faster, which means when they collide into each other, they are going to collide with more energy than the activation energy. The next factor we're going to talk about is surface area. So if you have more surface area, there is a greater chance that particles will collide. For example, if you put a large block of sodium in water, the only part of sodium that is exposed to that water is going to be the outside of that big block of sodium. Now, however, if you take that and you crumble it into a powder, that means every single particle that is now by itself has surface area. So that's going to greatly increase the surface area, which means that reaction is going to happen a lot faster because those particles are going to be colliding at a much higher rate. And then finally, we have catalysts. So there's 2 types of catalysts that are going to speed up reactions. There's homogeneous catalysts. Homogeneous catalysts are just mean that it's in the same phase. So like if you have aqueous and aqueous or gas and gas, those are going to speed up the reactions by providing an alternative pathway to complete the reaction that's going to take less activation energy. Then we have heterogeneous catalysts. Those mean that they're in a different phase. So like if you had a solid with an aqueous solution, those are going to speed up the reaction by altering the orientation of the molecules so the correct sides of the reaction can collide. All right, so let's do an example. So a student wanted to figure out the rate of reaction by measuring the rate that CO2 gas was formed from the reaction between HCl and CaO3. For the first part of this question, which set of conditions will cause the reaction to go the slowest? And it wants you to choose from each of the columns. The first column is CaCO3, and the options are small chips and powdered. For that set of conditions, we are going to choose small chips. Now, the reason small chips is going to cause the reaction to slow down is because there will be less of the CaCO3 exposed. So the next set of conditions is based on HCl. Now, we just went over molarity. When you have a higher molarity, you're going to have more particles, which means your reaction is going to speed up. So if we want the reaction to go slower, we're going to choose the lower molarity, which would be 0.005. And then our final is temperature. Remember when we talked about that last graph or that last table in the last slide? When you increase the temperature, you're going to increase the reaction rate because those particles are moving at a higher speed and then they're going to collide with more energy. So if we want the reaction to go slower, then we want to choose the ice bath. Now for B, it says A, but I meant B. For B, which set of conditions will cause the reaction to go fastest? It will be the opposite of everything we just went over. So it would be powdered, because that would give us more surface area. Then it would be our higher concentration, because that means more particles of HCl are present to collide, which will speed up the reaction. And then we're going to choose our warm water bath, because that is going to increase the speed of our particles, which means they're going to collide with more energy. All right, so let's do one more example before we move into 5.2. The rate of disappearance of ozone is negative 0.0034 molarity per second under a certain set of conditions. It is shown in the reaction there. What is the rate of appearance of O2 under the same conditions? So if it's under the same conditions, we can use basic stoichiometry to convert between our ozone to our oxygen gas. So what we have so far is given to us as 0.0034 molarity per second of O3. And we can convert that to O2 by just using our Bound's chemical equation. So we can go from moles of O3 to moles of O2. The only difference here is when we're talking about rate of reaction, we have to realize that if we have a reactant and it's moving towards the products, our coefficients for our reactants are going to be negative because, again, they're moving away from that. And then for our products, they're going to be positive. So for O3, it's not going to just be 2, it's going to be negative 2. And for O2, it will be 3 because it is a product, so it'll be positive. So when we solve for that, we end up getting 0.0051. It's going to be molarity per second of oxygen gas. That's because our ozone cancels out and our moles cancels out, so we're just left with molarity per second and oxygen gas. So that would be your answer for A. Then for B, we're looking at the rate of the reaction. So this reaction shown here is for one reaction. So we can actually use that stoichiometrically in order to solve for the rate of reaction. So we are given negative 0.0034 molarity per second of ozone. And we know that in 1 mole of reaction, we have negative 2 moles of ozone. So again, in 1 mole of reaction, which is this entire thing, we have negative 2 moles of ozone, and it's negative because it is the reactant. So if we look at our units here, our moles cancels out and our ozone cancels out. So we have the molarity per second for the entire reaction, which is the rate of the reaction. So when we solve for this in our calculator, we end up getting 0.0017 molarity per second for the reaction. So that would be our answer for B. All right, so 5.2 is an introduction to rate law. By the end of this lesson, you should understand that some reactions happen quickly while others happen more slowly. Your objective is to represent experimental data with a consistent rate law expression. And then you can go ahead and pause and read the essential knowledge if you would like. So since a rate of reaction can only be determined experimentally, we can use experimental data to write a rate law. This law is going to describe how the rate of reaction is proportional to the concentration of each reactant raised to a power. So just a very quick example, if you have D plus 2C reacting to form AB, an example rate law could be something like this shown here. The thing to remember here is that it could be, there's so many different rate laws for reactions just because it depends on the different factors in the different environments. So this is just one very simple example. Remember that anything expressed to the 0th power is going to be equal to 1. That's really important for this lesson and for this entire unit. This means that the reaction would be described as the 0th order in respect to D because it has a raised to the 0 power. And then with C, since it's raised to the 1st power, that means it's going to have a 1st order. So this means if that D changes in concentration, it is not going to affect the rate of the reaction. So if something is raised to the 0th power, that change in concentration does not affect the rate of the reaction. Now, if something is raised to the 1st power, like C here, that means if the concentration is doubling, the rate is also going to double. If the concentration is quadrupling, that means the rate is going to quadruple as well. Please note that the coefficients have nothing to do with the rate law. The rate law is only to be discovered experimentally. So the constant K is different for each reaction and set of conditions. The value for K is dependent on temperature, and it's known as the rate constant. So you will often be asked to solve for this value and provide the units. The units for K are going to describe the overall reaction order. Just please note that AP Chemistry normally only focuses on 0, 1, and 2 reaction orders. There have been very rare cases of 3 and 4, but most of the questions are in regard to 0th, 1st, or 2nd order. All right, so let's take a look at this example with A plus B reacts to form 2C. Looking at the data in the table, we can see that there are 2 experiments with the same value for A and 2 experiments with the same value for B. So when they are having the same value, that means that the concentration is going to be held constant. So if we hold A constant, we can inspect the data, and when A is held constant, B is going to be doubled, and the rate is also doubled. That means when you have the concentration and the rate equally increasing, that means you're going to have a 1st order. So B is going to be raised to the 1st power. So then when B is held constant, A is going to be tripled, and the rate is going to be increased by a factor of 9. So since 9 is equal to 3 to the power of 2, that means with respect to A, the concentration of A, it's going to be increased by the 2nd power, which means it's going to be 2nd order with respect to A. Okay, so if you had to solve for K, you can use this rate law, and you can use any of the rates from the experimental data. So we're going to go ahead and just use experimental 1. So our rate is 0.015 molarity per second, and that is going to be equal to K times the concentration of A squared times the concentration of B. So it'll be K times 1 molarity squared times 1 molarity. Now just remember, if you're using experimental 1 data, you have to use the concentrations from experimental 1 as well. So if you want to do our rate for experimental 2, then you'd have to use 1 for A and 2 for B. So now that we have that, we can go ahead and rearrange our formula in order to solve for K. So these 2 concentrations would combine to be 0.015 molarity per second equals K times 1 molarity cubed. So then to get K by itself, it would be 0.015 molarity per second over 1 molarity cubed. So when we get our final K, K would be equal to 0.015 over meter or molarity squared times seconds. And that's because our molarities cancel out. So this would be squared. And so then molarity squared and seconds would both be on the denominator. You're going to see this more commonly written as 0.015 molarity to the negative second power times seconds to the negative first power. So this is how you will normally see it written instead of like this. So that would be how you solve for K. All right, so let's do one more example before we finish out 5.2. So we have our reaction shown above, and then we have our experimental data for 3 separate experiments. So for A, what is the reaction order with respect to CO? So in order to figure that out, we want to look at where NO3 is constant. And NO3 is going to be constant between experiment 2 and experiment 3. So from experiment 3 to 2, we are going to multiply that concentration of CO by 4. So that's going to increase by 4. And if we look at the rate going from 3 to 2, that is also being multiplied by 4. So since the concentration and the rate are being multiplied by 4, that means they're going to be increasing at the same rate. So it's going to be first order. So the concentration of CO is going to be to the first order. So B asks, what is the reaction order with respect to NO3? So if we're trying to figure out NO3, we want to look at where CO is constant. And CO is constant between experiments 1 and 2. So from experiment 2 to 1, our concentration of NO3 is going to be doubling or multiplying by 2. And our rate is also going to be increasing by 2. So that means since our concentration and our rate are increasing at the same rate, that is also going to be first order. So it's going to be our concentration of NO3 raised to the first power, which is going to tell us that it is first order. So C says, what is the overall reaction order? In order to figure out the overall reaction order, you're going to you're going to add them together. So right now we have first order for CO and first order for NO3. So it's going to be 1 plus 1 or 2. So it's going to be second order. And then D says, what is the rate law for this reaction? So when we are talking about rate law, we know that's going to be equal to K times the concentration of CO to the correct power. In this case, we know it's first order, so it's going to be raised to the first power. And then times the concentration of NO3, same goes for that one, it's first order, so it's going to be to the first power. Now, you technically do not have to write the ones. However, sometimes it's nice to write them just to remember that it's not to the 0th order, it's to the first order. And then for E, it says, what is the value of K for units or with units? So you can use any of the experiments on this table. I'm going to go with the first experiment. So we have a rate of 1.68 times 10 to the negative second. That's going to be molarities per second. And that is going to be equal to K times the concentration of CO, which is 0.12 molarity. And then times our concentration of NO3, which is 0.72 molarity. So when we solve for k, we're going to end up getting a k of 0.194 divided by meters times seconds. So that's going to end up being meters to the negative first power times seconds to the negative first power. Again, you could have written it as 0.194 over meters times seconds, but this is going to be how you will see it on the AP exam, so that's just what we should probably be practicing. All right, so that is the first 2 lessons of Unit 5. I will shortly upload the remainder of Unit 5, but I wanted to get you started. I hope you have a great day, and I will see you tomorrow.